Welcome to course 1 of our data analysis series. If you are stepping into the world of data science, analytics or machine learning, there is one library you should absolutely understand, NumPy. NumPy is the foundation that powers data processing in Python. Behind Pandas, behind machine learning models, behind scientific computing, NumPy is working silently. In this course, we'll start from the very basics, what NumPy is, how arrays work, why NumPy is faster than Python lists, essential operations you will use every day, no overcomplicated math, no overwhelming theory, just clear beginner-friendly explanation designed to build your confidence. So if you are ready to understand the backbone of data analysis, let's begin. Alright, let's start with something simple but extremely important, that is importing NumPy. The line simply gives us access to NumPy library and the alias np makes our code shorter and cleaner to write. Next, we'll create a regular Python list. This is the standard data structure that you already know from Python. It can store in multiple values, but internally is just a collection of separate Python objects. Now let's compare that with a NumPy array. Here we convert the same numbers into a NumPy array. Even though it looks similar to a list, the structure is fundamentally different. A NumPy array stores data in a continuous block of memory, making it significantly faster and more efficient for numerical operations. Finally, we print both. And you will notice something interesting. They look almost identical when displayed, but behind the scene they behave very differently. A Python list is flexible but slower for mathematical computation. A NumPy array is optimized specifically for numerical processing, which is exactly why NumPy is called the backbone of data analysis. This small difference becomes incredibly powerful when working with large datasets, performing calculations, or building machine learning models. So remember, same appearance, completely different performance. Now let's create our very first NumPy array. We are using NumPy array function to convert a Python list into a NumPy array. Inside the brackets, we provide values 10, 20, and 30. NumPy takes this list and transform it into a structured, efficient numerical array. Next, let's print it. And the output looks like this. Notice something subtle but important. NumPy prints elements without commas. This is one visual clue that you are working with an array, not a list. But what's really happening behind the scenes? NumPy stores this value in a contiguous memory block. This makes operations like addition, multiplication, and statistical calculations extremely fast. Why does this matter? Because in real world data analysis, you might work with thousands or millions of numbers and performance becomes critical. So this line is your gateway to a high performance numerical computing. Simple syntax but powerful capability. Let's move one step further and create a two-dimensional NumPy array. So here's the code. At first glance, this looks like a list inside another list, and that's exactly what it is, a nested list. NumPy interprets the structure as rows and columns, forming a matrix-like layout. So what we have here, first row 1, 2 and 3 and the second row 4, 5 and 6. This gives us a table with 2 rows and 3 columns. Next, let's print the array. You can see the output. Notice how NumPy neatly aligns the value representing the grid structure. Why is this important? Because most real-world datasets are naturally two-dimensional. Excel sheets, CSV files, database tables, machine learning feature matrices. NumPy arrays are designed to handle this type of structured data efficiently. Instead of working with complex nested lists, NumPy gives us faster computation, easier slicing, built-in more mathematical operations. So whenever you think of dataset, think rows and columns, 2D NumPy arrays. This is where data analysis truly begins. Now let's explore something incredibly useful functions in NumPy, special arrays. These are arrays we generate instantly without manually typing the values. So this creates an array entirely filled with 0. The 2, 3 specifies the shape, 2 rows, 3 columns. Perfect for initializing placeholder, mask or empty dataset. Next, as you might guess, this creates an array filled with ones and the shape is 3 rows and 3 columns. Arrays of ones are commonly used in mathematical operations, scaling and matrix calculation. Now, the one that I am going to type is extremely important. This generates a sequence of numbers automatically. Start at 0, stop at 10, which is not included, and the step is 2. So the output will become, let me print them. So the output becomes 02468. This is very similar to Python's range function, but returns a NumPy array instead of a list. Finally, you can see I have printed them and this is the output. And we get 3 different arrays instantly. So why does these functions matter? Because in data analysis and machine learning, we often need initial arrays, test data, structured numerical sequences, matrix templates. Instead of writing loops, NumPy lets us generate them in one line. Less code, more efficiency, cleaner workflows. Now that we know how to create arrays, let's learn how to inspect them. So here's our array. You can see the formula array.np.array and followed by the value. A simple 2D array with numbers. Now we explore 3 important attributes. First, let's print the shape of the array. This tells us the structure of the array. The output will be 2, 3, meaning 2 rows and 3 columns. This is crucial in data analysis because many operations depends on correct dimensions. Next, let me show you the number of dimensions. This shows the number of dimensions and the output is 2 because this is a 2D array. Remember, 1D is a vector, 2D is a table or a matrix, 3D is multiple matrices like image or time series. Finally, let's reveal the data type of elements inside the array. The output is int32, which means that the NumPy has stored this value as 32-bit integers. Why does the dtype matter? Because NumPy arrays are homogeneous, all elements must be of the same type. And choosing the right type impacts memory usage, computation speed, numerical precision. So these 3 properties, shape, dimensions, data type, are your basic diagnostic tools whenever you work with NumPy arrays. Always inspect your data before performing analysis. Now let's arrive at one of NumPy's most powerful features, vectorized operations. So let's start with an array. A simple one-dimensional NumPy array. Now watch what happens. NumPy adds 10 to every element. So you can see the output 11, 12, 13 and 14, which is addition of 10 to every element in the NumPy array. No loop, no manual iteration. Next, we will get each element multiplied by 2. And finally, the square of each value. This is called element-wise computation. And why is this a big deal? Because with Python list, you normally need loops for I in list, do calculation. But NumPy performs these operations internally in an optimized code, which means much faster execution, cleaner code, better readability. And this becomes extremely important when working with large datasets, mathematical modeling, statistical analysis, machine learning. Instead of writing very complex logic, you simply write array plus value, array into value, or array square of any value. Simple syntax, high performance. This is exactly why NumPy is the backbone of data analysis. Let's learn how to access data inside a NumPy array using indexing and slicing. So here's our array, a one-dimensional array with 5 elements. So first, let's retrieve the first element. The output is 10 because NumPy uses zero-based indexing just like Python. Now let's retrieve the last element. The output is 50. Negative indexing counts from the end. Very useful when you don't know the exact length of the array. Now slicing. The start index is 1, the stop index is 4, which is not included. So we get 20, 30 and 40. Notice that the start is included, but the stop is excluded. Exactly like Python slicing. Why is slicing important in data analysis? Because we constantly work with subsets of data, feature selection, training versus testing splits, filtering ranges. So instead of writing loops, NumPy lets us grab large chunks of data instantly, clean, fast, and efficient. Mastering indexing and slicing is essential for working with real datasets. Now let's explore indexing in 2 dimensions. So let me type a 2-dimensional array. So this is a 2-dimensional array. Think of it like a table. Row 0, 1, 2, 3 and row 1 has 4, 5, 6. Now let's look at this line. This row uses row and index column. First value is the row number, second value is the column number. So what are you selecting? Row 0, 1, 2, 3 and column 1, which is 2. The output is 2. Simple but extremely powerful. Because in real world datasets, the row stands for observation and records, the column stands for features and variables. This is how you access a specific value inside your data. For example, a student score, a product price, a sensor reading. NumPy allows precise, fast data access using array, row followed by column. No nested brackets, no overcomplicated syntax. Clean and efficient, just how data analysis should be. Now let's unlock one of NumPy's biggest advantages, built-in statistical functions. So let me add a data set. You can see I have added a NumPy array in the form of a data. So let's perform a simple numeric. It's a simple numerical array. So let's print it. This calculates the average value. The output is some 30. NumPy quickly sums the value and divides by the count. Now let's compute the total sum. The output is 150. Next, let's find the largest value. The output is 50. And finally, let's return the smallest value. The output is 10. Why are these functions important? Because statistical calculations are everywhere in data analysis. Averages, total, maximums, minimums, performance metrics, feature summaries. Without NumPy, you would need loops or manual calculations. With NumPy, one function call gives you an instant result, fast, readable, and reliable. And this is just the beginning. NumPy also supports standard deviation, variation, percentiles, median, which we will explore later. For now, understand, NumPy is not just about arrays, it's a powerful numerical analysis engine. Let's apply what we have learned to a simple real world example. Let me add an array where we have student marks. This NumPy array represents scores of 5 students. Now let's analyze this data. Let's calculate the average marks. You can see that the average is 73.2. This calculates the average marks, a common metric used in performance evaluation. Let's find the top score, useful in identifying best performers. Now let's do something very powerful. Let's do a conditional filtering. So let's break it down. If the marks is more than 60, it creates a Boolean array which is false, true, true, true and true. NumPy then selects only value where the condition is true. So the output will be 72, 68, 90 and 81. These are all greater than 60. No loops, no complex logics. This is called Boolean masking and it's heavily used in data analysis for filtering, removing outliers, selecting categories, creating subsets. This is a tiny example that reflects the real analytical workflows. Calculate statistics, applying conditions, extracting insights, and that's exactly how NumPy helps us think like a data analyst. And that wraps up the course one, which is NumPy fundamentals. So today we have learned how to create NumPy arrays, the difference between list and arrays, array properties like shape and dimensions, vectorized operations, indexing and slicing, basic statistical functions. These are building blocks of everything you will do in data analysis. But remember, watching is not enough. Open your notebook, write the code, experiment with your own numbers. That's where real learning happens. If you found this video helpful, don't forget to like the video and subscribe for the next course, where we'll dive deeper into NumPy operations. Keep practicing, keep building, and I'll see you in the next lesson.